record on, and then I want to pause it.
Okay. Okay, thank you everybody for joining us for our second Tech Talk. We have the pleasure of getting information from Dr. Ilkka Lähdesmäki, the Chief Scientist of FIA Lab Instruments. He's going to give us his insight into flow injection chemistries and techniques, because that particular automated system is becoming quite popular now in laboratories. So we want to give you the expert's opinion of this particular topic. I'm happy to introduce you to Dr. Ilkka Lähdesmäki. So take it away, Ilkka, please.
Thank you very much, Carolyn. And hello, everybody. Thank you for making the time to attend the talk. I'll just wanted to open my video for a little while to say hi, and then probably shut it off again and go. Let's go ahead and share my presentation, and then we can get going. Here we go. All right. Hopefully everybody can see my screen okay.
Excellent. Yes.
Good. So the topic of today's talk is flow injection analysis. And the way I think it was spelled out in the invite was flow injection chemistries and techniques. The way we've put the talk together, we're going to start with a little bit of history into the general field of flow analysis. We'll talk about the fundamental operation principles of flow injection, discuss why FIA ended up becoming adopted as a practical analysis technique that we know it today. Linked to that, we'll discuss practical benefits that FIA gives operators and labs employing it. We'll take a glimpse into a case study to highlight practical instrument and method design that sometimes can deviate from the theoretical principles to provide a practical benefit. And then finally wrap up with conclusions and questions. That's me and my contact information. If you end up having questions that you will not think of or do not want to ask during the talk, but want to shoot me an email afterwards, you're more than welcome to do that. And with that, we'll start. So first, history. If we take a step back into the origins of colorimetric assays for wet chemistry, it all started, not too surprisingly, in a manual format. So these would be methods that a lab analyst would run on the benchtop using pipettes, beakers, cylinders, volumetrics, whatnot, to aliquot a volume of sample, mix it with color-generating reagents and buffers and so forth. If needed, if you had a sluggish reaction, you could speed it up by placing the glassware on a heated water bath. And at the end, when you let it sit and a color has developed in response to the presence of analyte in the sample, you would pour the colored solution into a spectrometer cuvette and measure the color intensity on a benchtop spectrometer. These manual methods were simple, they were robust, but on the flip side, they're quite time-consuming and laborious because an analyst intervention or analyst action is required for every single step along the way. And it's not too surprising that once labs had been using these methods, there was a need to get them automated somehow. The first way of doing that was invented in the 1950s by a scientist called Dr. Skeggs. He developed an instrument that was able to do colorimetric wet chemistry in an automated manner. The instrument was quickly commercialized by the Technicon Corporation in the 60s and became the best-selling instrument of its time, more or less. The premise of it was that you did the automation with the aid of continuous moving liquid flow streams. So you'll basically have a stream of sample that then gets mixed in with streams of color-generating reagents. In order to propel the motion of these liquid streams, Dr. Skeggs was using a peristaltic pump hooked up to an autosampler so that he could pick up various standards and samples in an automated manner. In place of traditional glassware containers, all the mixing and all the reactions were happening inside glass coils and glass tubing. Very importantly, besides mixing in liquid streams, the instrument also included a stream of air so that the flow got broken up by little segments of air bubbles or air pockets. Dr. Skeggs deemed this segmentation necessary so that the sample slug would not spread out uncontrolled inside the tubing, but the air pockets would act as barriers that keep the sample segment confined. Instead of a water bath to heat slow reactions, the instrument used a flow-through type heater, basically a heated chamber where you would place one of these glass coils. Color measurement was, of course, not done on a benchtop spectrometer, but inside a flow-through cuvette or flow-through flow cell. That's Dr. Skeggs' invention. Schematically, the instrument would look something like this, where, let me get a pointer here. You can see how we have an autosampler on the left, and the autosampler probe is connected to a pump line that's continuously drawing sample from whatever cup the sampler probe happens to be in. You have separate lines of the different reagents that are necessary to combine with the sample to make the color reaction happen. And then you have a stream of air that gets mixed in to break up the liquid flow and that way keep the sample segment confined. Over here, we have a schematic of a flow-through heater coil where, as I remember mentioned earlier, you can use heat to speed up slow reactions. Then one important aspect regarding the bubble segmentation is that in a traditional flow analyzer, you can't allow the bubbles to enter the detector flow cell. Otherwise, you would get tremendous disturbance signals and you would never be able to get anything sensible out of the detector. So the instrument had to include a component called the bubbler that removed the air segments while allowing the liquid portion to proceed over to the detector. And that's here represented by this inverted triangle. Finally, at the end of the line, you have the detector cuvette where you make the color measurement. So that's how a segmented flow analyzer would look schematically. Our next step includes discussing the flow injection analysis technology that is the meat of this talk. This was invented a little less than 20 years later, 1974, by Dr. Ruzicka and Dr. Hansen at the Technical University of Denmark. This technology as well was commercialized quite quickly, initially by a small Swedish company called Bifolk, which later became or was acquired by Decatur. The premise was still very much the same in the sense that you're still mixing the sample with color-generating reagents using liquid streams. Also, you're still using a peristaltic pump to power the motion of the liquids. But an important distinction between FIA and segmented flow is that you're not using a continuous sample stream inside the instrument. Instead, you're employing an injection valve to meter a segment of sample into the instrument. And in this sense, flow injection works in a manner that's very similar to liquid chromatography or ion chromatography. The containers inside which all the chemistry happens are still coils and tubing, but FIA uses Teflon as the coil and tubing material as opposed to glass. Very importantly, FIA does not use any type of air segmentation. What's flowing inside an FIA instrument is only liquids. Heated incubation is still done with a flow-through heater, and color measurement is still done with a flow-through cuvette or the flow cell. Then let's take a look at the way that an FIA instrument would look schematically. Here too, there are a lot of similarities in the sense that you originate at an autosampler where the probe goes inside a sample cup, and there's a pump line that provides suction so that the sample travels through the connecting line and then gets to an injection valve. If the valve is in its load position, the sample flows into the valve and fills a sample loop on the valve, after which the valve can flip from the load position to an inject position, and the sample now becomes part of the path of a continuously moving carrier stream. So the carrier is going to go in, push the sample segment out of the sample loop, and start pushing it along the instrument's manifold, where we're going to mix in the first reagent with the sample, go through a mixing coil, mix in the second reagent, go through another mixing coil that's possibly heated, and then go on to the detector for color measurement. Hopefully, that makes it clear how an FIA instrument works and how it's principally different from segmented flow analysis. All right. Now, let's go a little deeper into the operation principles. You see a familiar schematic here that shows you the FIA instrument. And what I wanted to address in this slide are the three pillars or tenets or operation principles that the FIA operation rests on. The first one is precise injection. An FIA instrument only meters a relatively small amount of sample into the instrument. And it's very critical that the sample volume remains the same from one measurement to another, to another, to another. Presently, this is possible thanks to the tremendous technical development that has taken place over the last 30, 40 years in the field of injection valves, as it was necessary for ion chromatography and liquid chromatography purposes. So that part we've got taken care of. The next point is controlled transit time. In order for the color to develop to the same degree for each sample, it's important that the time that a sample spends inside the instrument between the point of injection and the point of detection remains the same from one measurement to another. This is something that relates more than anything else to the peristaltic pump, where also present-day technology fully allows this repeatable timing to take place. The last pillar is called controlled dispersion, and it begs the question, what is dispersion? Dispersion really is a fancy word for dilution, and in order to understand it, let's take a look at the bottom left part of the schematic, where we have a view of the sample zone shown in blue color, carried by the carrier stream showed in yellow color. As you can imagine, as the carrier keeps pushing the segment of sample inside the tubing, the sample is continuously getting diluted or smeared out into the carrier. And that way, the sample is getting progressively more diluted the further it gets into the instrument's manifold. The degree of this dilution and the process of this dilution from the edges is called dispersion. And it's important that the FIA instrument, and specifically its fluidic manifold, is well designed so that this dispersion process that the sample experiences remains the same from one sample to another. So these are the three principles that need to be sound and fulfilled in order for the FIA instrument to work well. Precise injection volume, steady transit time, and controlled dispersion or dilution. The dispersion process is the reason why almost all the time signals from an FIA instrument are in the shape of a peak. It's the same way as in liquid or ion chromatography. It's because you're only injecting a relatively short segment of sample that gets diluted or dispersed into a peak, and that's the shape that comes out of the detector. In order to quantitate your color intensity, you can either use peak height or peak area as a metric. Which one you pick is more or less a matter of taste and what each lab is used to from their past practices. Okay. I'm hoping that at this point you'll have a decent understanding of what an FIA instrument looks like and how it operates. Then let's ask ourselves the question, why did FIA become adopted? The fact of the matter is that by the time FIA was invented, there was already the mature and widely spread technology of segmented flow analysis established all over the world. If FIA did not offer any advantages, why would it even be used at all? And it's very interesting that when Drs. Ruzicka and Hansen initially invented FIA, they offered that concept to the Technicon Corporation, the commercial entity behind segmented flow analysis. And as per Dr. Ruzicka, Technicon's response was quite negative. Their patent attorneys said that it's not patentable, so it has no legal or business value. And their technical folks said that this new invention was completely impractical and is never going to become a real method of analysis, so it's of no interest to Technicon. That's pretty stark comments on this new invention from the people who were the world's experts in the field of flow analysis. And against that background, we do have to ask the question, why would FIA survive? When I thought about it, these are the things that I can come up with as a way of explanation. One is speed. In its extremes, a FIA instrument can be tuned up to run up to 300 samples an hour. Of course, at that speed, you're not going to do extreme low-level analysis, but this speed is attainable even for some practical analysis cases where low-level analysis is not of high importance, but analysis speed is of absolute highest importance. There's another speed aspect where FIA provides an advantage as well, and that's calibration speed. Many times in FIA, you can get the calibration done within 5 minutes, maybe up to 10 minutes. And that's a tremendous benefit when an analyst wants to get the instrument running. They want to make sure that their calibration worked out okay, the QCs came out okay, and then they can go off and do other things. This stands in contrast to most segmented flow methods where you have to wait for 20, 30 minutes until you know how your instrument is running. A further advantage is the lack of carryover. In FIA, you have complete return to the baseline between measurements, while in SFA, you rarely come all the way to the baseline between peaks. And for that reason, you tend to have a lot of need for reruns, especially in cases where a low-level sample followed a high-level sample. And now the low sample is basically riding on the tail of the high sample, and getting it accurately quantified is not really possible. The fourth advantage is seemingly small, but actually quite significant in practical terms. When you're using Teflon, tubing, and coils in place of glass, you have something that's extremely inert. Glass is inert, but I think Teflon is probably the most inert material of all. It's also much, much, much less breakable than glass, and therefore provided a big practical advantage over the traditional segmented flow and its glass coils. All right, let's now expand on those practical benefits that we already started discussing. What can flow injection provide a lab? Increased speed and sample throughput. This is especially important for high throughput labs. FIA Lab has some customers that in their busiest season, they run thousands of samples every single day. And in that case, every second matters. And our record of setting up FIA methods and FIA instruments is an orthophosphate method where we ran samples every 8 seconds. As I mentioned earlier, you would not be able to do that kind of speed and do low-level quantitation or absolute highest precision. But this happened to be an application area where you don't need to be tremendously precise and you never need to go low. So this 8-second time frame ended up working on a practical level to the point where the customer needed it to work. We also discussed the increased calibration speed, where FIA can get a calibration done in 5 to 10 minutes. This is an aspect where we tend to hear comments less from lab managers, but almost always from lab analysts. because it's a tremendous benefit for their everyday operations. There's been several cases where FIA Lab has replaced other instruments, and the analysts are saying this is so great. The calibration takes no time at all, and I know immediately whether my run worked out or not. And it just matters a lot to them. As with any automated technology, a benefit of automation is decreased labor. Whenever you have to do something completely manually, it takes a lot of staff resources in terms of staff time. And with automation, you can assign that staff to do other things. Another part of that is increased efficiency, where a given staff member might still have to dedicate their time to a FIA analyzer on a given day, but they can do so in a manner where they set up their run, get it going, make sure that the calibration and the QCs are passing, and then they can step away and do other things while the bulk of the run is going. Only briefly taking a look at the instrument to make sure that everything is still running okay, but being able to get much more done in the same time frame compared to a situation where they would have to run this method totally manually, in which case there's nothing else they can do that day. And the final point has to do with the way that an FIA instrument can handle challenging sample matrices that are high in acid, have coloration, high in base, etc. This can typically be done with membrane units like a gas diffusion block or a dialysis block, where you can exclude or at least minimize that color or acid or base interference, which could be very tricky to do in a manual setting. So that would be a list of practical advantages that a lab can gain from using a flow injection analyzer. All right. At this point, maybe I should ask if there are any questions on the principles or practical advantages before we go on to discuss our case study of practical instrument and method design. If not, then on we go.
No questions in the chat, Ilkka. Thank you.
Perfect. Thanks. So what we chose as our case study is an ammonia/TKN method based on a chemistry called OPA, short for orthophthalaldehyde. This is a method that FIA Lab has put together and worked with the EPA Clean Water Office on to get it EPA approved, which it presently is. And a central part of the instrument setup we chose to that end is the concept of gas diffusion. So let's spend a little bit of time to discuss how gas diffusion works for ammonia measurements. You can see a schematic of it over here. You'll have a two-block or sandwich arrangement gas diffusion cell over here, where its two halves are separated by this gas permeable membrane shown in orange color. On the lower portion, the so-called donor side of the sandwich block, we're bringing in a solution where we have a stream of sample that contains ammonia, probably in the form of NH4+, and then another stream that contains an alkaline reagent, sodium hydroxide typically. Once you mix the two, you're going to shift the pH conditions in the sample into the alkaline region, rendering ammonia volatile, because you're converting NH4+ into NH3, and NH3 is the volatile, smelly form of ammonia. once that alkaline solution enters the donor compartment, it comes in contact with the gas permeable membrane, and now volatile ammonia can diffuse across the membrane over to the acceptor side, while all the liquid and solid components in the sample are just going to go straight through the donor chamber into waste. The acceptor part is being flushed by another solution that now picks up the ammonia that diffused across and pushes it out and into the remaining part of the instrument manifold. That's how gas diffusion works. Make ammonia volatile, bring it in contact with the gas diffusion gas permeable membrane, pick up the ammonia that diffused across the membrane over to the acceptor side. And then another piece of background information is the OPA chemistry. The OPA reaction between OPA and ammonia is shown here, where you have the ophthalaldehyde reagent that reacts with ammonia in the presence of sulfite, generating this fluorescent compound that we can now measure by shining UV light on it and measuring the blue glow that this compound has when it's being illuminated by UV light. And as you can tell from that, this detection technology is a little bit different from the traditional colorimetric analysis in the sense that we're not measuring absorbance, but fluorescence. The advantage of fluorescence being that since our illumination light in the UV is in a different spectral region than the emission light that we're collecting, we're able to optically isolate these two light ranges, and that way make our measurements against a dark background, giving us tremendously more sensitive measurement conditions compared to absorbance. And here's how the OPA ammonia TKN instrument would look. We have the gas diffusion cell here that we just discussed, and otherwise it's very much like the traditional FIA schematic that we saw a few slides back. You have a carrier solution up top that takes care of pushing the sample out of the injection valve sample loop and transporting the sample along the instrument's manifold. We have a solution of sodium hydroxide that we're mixing in to make ammonia volatile. Then we have the gas diffusion cell that's there for ammonia to diffuse across the gas permeable membrane. And finally, we have a solution of OPA that flushes the acceptor side of the gas diffusion block and then takes the ammonia onwards to a heated coil and then to the fluorescence detector. The two aspects that I wanted to discuss for instrument design are the choice of heater length on the flow-through heater, and then the choice of acceptor solution for the gas diffusion block. So let's first take a look at the choice of the acceptor solution. Traditionally, in any kind of ammonia distillation protocols, conventional wisdom states that the acceptor has to be an acid solution. Whenever you distill ammonia, you make the conditions alkaline for the distillation vessel, and you use an acid absorber solution. Yet, here we chose an alkaline solution having borate buffer and OPA in it. The question is why? The answer is for reasons of simplification. By using the OPA solution as an absorber, we were able to simplify the manifold and make a much more compact and simple instrument. That way, giving practical benefits to the operator who uses it. The other option would have been to use a separate acid stream as an absorber and only then bring in the OPA solution. But now the manifold would have been significantly more complex. The other point of discussion was the choice of heater coil length. The OPA reaction is quite slow, so technically, the longer coil you had around the heater, the more contact time the sample would spend with the heater, and the higher the degree of the color development would be. Yet, we chose a relatively short coil of 70 inches, and this we did to get as much calibration speed out of the instrument as possible. Had we chosen a really long coil, yes, that would have increased the response, but it would have come with the price tag that now the coil is so long that you're going to have to wait quite a long time for each sample to go through the coil. And now that quick calibration that has been the trademark of FIA instruments would have gone at least partially out the window. So these I wanted to discuss because they illustrate the point that while it's always very, very good to keep first principles and fundamental ideas fresh in your mind when you're developing an instrument or a method, at the same time, you also have to weigh practical benefits and try to strike a balance between the two. By adopting this simplified manifold, we were able to implement the OPA ammonia TKN method on our smallest instrument, the fertilizer 1000, so that the instrument setup basically just measures more or less 10 inches tall and 10 inches across, give or take. And that's quite a big benefit for labs that tend to have limited bench space, that you can now set up your ammonia TKN measurements on a minimal footprint in your lab. Of course, when you're giving up some of the fundamental ideas, you need to be very careful in validating the method to make sure that it still works. It's pointless to have all of these nice practical ideas if the outcome is that you have a method that works poorly. As I mentioned earlier, we collaborated with EPA to get the method validated and demonstrated that it can span quite a wide dynamic range for ammonia measurements. And it had very, very good accuracy when we subjected several practical water samples for analysis on this method. Some of them were samples from different parts of water treatment processes, and some of them were naturally occurring water samples. And the final thought that I wanted to leave you with after all this discussion of practical instrument design is a quote from the father of analytical chemistry, Dr. Piet Kolthoff: "Theory guides, experiment decides." Analytical chemistry, more than anything else, it's an experimental science, and I think nothing highlights it better than this quote by Dr. Kolthoff. With that, I'd very much like to thank you for attending, and now it's time to take any questions that you might have.
It looks like we have a question from Robert in the chat. Have you done much work with brackish or saline waters that cause baseline disruption?
Yes, that's an excellent question. And there are a couple of answers to that. So that's one of the reasons why we implemented this particular method with the gas diffusion setup, because that isolates your sample from the detector and greatly reduces any artifacts that brackish or saline matrices would have on the response. The other part of it is that the fluorescence detection technology to begin with is less sensitive to saline brackish variations than absorbance detection would be. So that would be my first answer relating to this particular method. Then if we broaden the answer to cover other methods than this particular OPA-based ammonia method, yes, we have worked with that, and that can be a very challenging area. The way we've addressed those is, first of all, it helps that FIA Lab uses so-called array detectors for our color measurements, where we are able to utilize other wavelengths than the wavelength where we're monitoring to put in place background correction protocols that attenuate fluctuations caused by brackish matrices. And we've also put in place, in extreme cases, special flow cells that are optically designed in such a way that they attenuate, in many cases, completely eliminate the refractive index variation, or the effects of the refractive index variations that you get from saline and estuarine samples.
Excellent. Thank you for answering that. We have a couple more questions. We have one from Chris Francis. Is the 50 micrograms per liter limit quantifiable, but the method can detect concentrations below?
Yes, that is correct. And I should clarify that that was the quantification limit for the particular configuration that we were working with in the EPA validation efforts. And that configuration was actually not at all tailored to low-end analysis, but more tailored to high-end analysis, because that seemed to be where a lot of the lab's needs were. They wanted to extend the calibration range as high as possible on the high end and did not care so much about the low end. If need be, that method can easily be reconfigured with a longer sample loop so that you can reach a quantitation limit of, let's say, 10 ppb and a detection limit of single ppbs.
Okay, we have another question. If this works on wastewater, do you have a cleanup or extraction steps? And that was from G. Haleb.
Yes, this works for wastewater, and extraction is not necessary. Cleanup for very turbid samples, yes, I would recommend that you either centrifuge or filter the samples if there's a high degree of solids in them.
Okay, and two additional questions from G. Haleb. What is the lower detection limits for ammonia is the first one.
So That goes, let me go back a couple of steps here. So for this particular configuration, hopefully the slide is still visible. The detection limit was 12 ppb and reporting limit was 50. But as I mentioned earlier, if there is a need to go lower, that is easily done by just increasing the sample loop size, so that you should be able to go to something like a reporting limit of 10 ppb and a detection limit of 102 ppb.
Okay, and then one last one from G. Haleb. Do you have a dedicated instrument for detecting different analyte?
That depends a little bit on the instrument platform. So in general, we do recommend that having dedicated instruments makes the analyst's life a lot easier. And on our fertilizer 1000 instrument platform that's shown here, we strongly recommend that you always run these dedicated. We have another instrument called the Fertilizer Flex. Like its name suggests, it was meant for being more flexible. And we designed it so that it's very easy to switch back and forth between chemistries if that's what the customer would like to do. Hopefully that addressed the question.
I believe so. And then we had a comment that was answered in chat in case you can't see it from Caitlin Rain. Has this OPA modification been promulgated in the 40 CFR 136 Clean Water Act for TKN and NH3 by flow injection? Yes, this method is currently listed in table 1B for both ammonia, number 4, and total, I'm going to butcher that, Cledgehol nitrogen, number 31. Apologies if I mispronounced that. We have, and then another question from Chris Francis. What is the replacement schedule for the gas diffusion apparatus and what affects this?
The replacement schedule for the gas diffusion membrane, somewhat depending on the sample, ballpark, I would say maybe once a month. And what affects that is, if you run a lot of turbid samples, the pores on the membrane can get clogged. Maybe if you ran a whole lot of samples that were very high in oils, greases, detergents, that might also affect the gas diffusion membrane by making it soluble to or permeable to everything. But more than anything else, it's the particulates clogging the pores. And what we've seen among our customers is that I would say about once a month would be the exchange protocol for the membrane.
Excellent. Thank you, Ilya. Another question from Tara McClinton. How long does it take to calibrate and analyze a batch of samples, let's say 20?
Let's say 20. Well, let's take a look here, because I had, so this would be 1, 2, 3, 4, 5, 6. So this is about 10 samples, and that gets done in the span of about 700 seconds. So it's ballpark, I would say, a sample a minute. So 20 samples, 20 minutes plus, of course, the prep time.
Wow, highly efficient. From Katie Rain, can you share a list of labs currently running this OPA method?
Yes, so that would be something where I would probably refer to our sales team, because we usually ask for customers' permissions before we share their contact information or even share them as a reference. And I think the sales team probably has done that with our existing customers. So if we can get an email address, then I'm sure that Jordan can work together with the rest of the sales team to provide feedback and share some lab locations where this method is being run. We've installed it quite a bit since we got it approved in the 40 CFR Part 136, and have a lot of very happy customers running it. So there's going to be no problem providing references. We just have to make sure that those are locations who have allowed us to share their name.
Is there a best email that could be inputted into the chat for people to reach out to?
Yes. There we go.
Thank you for that, Ilkka. And it looks like we have another question from Tara McClinton. What is the replacement cost of the gas diffusion membrane? Is it available through other vendors?
It's available, of course, through us. It is available through other vendors probably as well. The issue is that there are many vendors selling something like that. You just need to make sure that it's exactly the right kind. And the cost, I don't remember exactly, but it's probably, what would I say, very, very crude ballpark, $10 a piece or something like that.
Excellent. And then one more comment, it looks like, from G. Haleb. Is this method number in 40 CFR 136?
Let's see. Can you repeat that question, please?
Of course.
I can read my question. Probably wasn't very clear.
Yes,
So
please, please. Do.
I said I was just wondering what is it listed under, like a method ID in 40 CFR 136?
Yes, it's listed under 40 CFR Part 136, and the method ID is FIA 100.
Oh, ELAB 100?
FIA. I can type it here.
Oh, yeah, okay. Okay, thank you.
And looks like Tara also had a follow-up question to her previous, what is the replacement process of the gas diffusion membrane?
That's a great question. And that's something that we've paid a lot of attention to, because if there are anyone in attendance who's run a latchet gas diffusion method, the membrane replacement process is extremely arduous. And we have a gas diffusion unit where, for an experienced operator, I think it takes about 20 seconds. You're basically that sandwich block assembly is held on by a cam lever. So you just lift up the lever, slide it out, then you can separate the two halves, take out the membrane, put a new membrane in, slide the top block on, and close the lever, and you're done. And maybe let me see if there was, yeah, on this slide, you can see, let me bring back the laser pointer again so that I can highlight. Here is the gas diffusion block, and this curved metal part is the lever that I was talking about. So you would just lift this up, then you can slide this top block off of its rails. The rails are these metal parts over here. So the top block slides off. That gives you access to the membrane. You peel off the membrane, you put a new one back on, slide the top block back in, then slide in the lever and close the lever, and you're in business.
Excellent. Looks like we have a feedback comment from Chris Francis, as well as a question about a follow-up presentation. This has been a great presentation. Would it be possible to have a similar presentation on the software, including how the software integrates? It's a great question.
Yeah, absolutely. That would be possible. We can schedule that at a later date.
Beautiful.
We'd be very happy to do that.
Excellent, excellent. Well, we'll include that in a future Tech Talk. Any other questions via chat or via hand raising? Looks like we had Caitlin raise her hand. Go ahead, Caitlin.
Hi, yes, my name's Catherine, but thank you.
I'm so
Ilkka,
sorry.
no problem. I'm actually curious. So I see that you do TKN and ammonia by this OPA method modification, but I'm curious if there's any other nutrient analyses that are, I guess, possibly able to be analyzed by this method modification as well, or if this is just exclusive currently to like the nitrogen-based nutrients.
So this particular method only addresses TKN and ammonia. But of course, FIA Lab has methods available for all the other regular parameters that wastewater labs are measuring by FIA. So orthophosphate, total phosphorus, nitrate, nitrite, phenol, cyanide, chloride, sulfate. We cover them all.
Okay, thank you very much.
Okay, I think that's all we have for questions. Carolyn or Rachel, if you're still on the call, if you want to do a little close-up comment.
This is Rachel. Yeah, thank you to Dr. Lähdesmäki for presenting today. We really appreciate it, and we will follow up on that idea of having you present on the software. And thank you everyone for attending. I hope that you learned something. If you do have any questions, as it was indicated in the chat, you can email FIA Lab, or you can also email info@calanalysts.org, and our emails on the website, and we can always put you in touch with a presenter or anyone else. Please do also use our email to send us ideas for other presentations that you'd like to see. We're really excited about this Tech Talk series, and it gives us a chance to, hopefully target our goal of sharing information and asking questions and giving tips to each other in our community. So thank you, everybody.
Robert, was there something you wanted to add?
No, I'm set. Thank you so much. I thought that was a fantastic talk.
And on FIA Lab's behalf, I would also like to thank Robert and Rachel and Jacqueline and everybody who worked together with us. We really appreciate the opportunity to present. And I must say that the mechanics of organizing this were done excellently. So it was minimum burden on me and everybody at FIA Lab because of the work that you guys did ahead of time.
Thank you very much.
Thank you so much, everybody. Thank you,
Appreciate it,
Doctor.
Thank
Ilkka.
you.
Okay, take care, everyone. We hope to see you on future Tech Talks. And again, please email us with any questions, comments, or ideas for future talks. And we'll see you online. Take care, everyone.
Have a great
Bye,
day.
everyone.
Bye.
Bye.
Thank you.